Hello and welcome back to Danfoss Drive School at the Marine Competence Center in Holmestrand, Norway. This is the episode 5 on the marine application and permanent magnet motor setup. You should have seen through episode 4 with the basic setup and open loop settings. This episode 5, we are going to look into the closed loop IF control, sensorless and overspeeding. The closed loop on a marine application is basically a speed regulator. It's not a positioning regulator. We have a feedback from a resolver or incremental encoder to the option board in the drive, and it will try to do the most precise speed that the order is for. For positioning systems, like advanced winches, active heave compensation and so on, usually the closed loop in the drive is this one. And then you have a PLC control system that calculates positioning and motion control. The encoder board in the drive must be put in the slot C. In this case, we have a resolver in the Editron motor and the board is opt BC. Here we see that the jumpers need to be set to a specific setting. If we look at the jumpers, this is the amplification of the sinus cosinus. This is the excitation voltage 7 volt, because the signal on the resolver looks like this. You have an excitation of 10 kilohertz, 7 volt amplitude, a sinus and a cosinus signal. It's actually a positioning signal. It's not really a speed signal because the drive calculates the speed out of the positioning. The reason why it's positioning is that the drive needs to know the polar angle where the magnets are. So traditionally the resolvers are for positioning and identification of the polar angle. With the Editron motors, the resolver will have the same pole number as the motor itself. So this is a 6-pair pole motor, and the resolver is actually the same. So actually it's mounted synchronous to the magnets. You can actually use the same shaft angle parameters for all of them. So identification of the encoder, you can copy it from another drive. The cable itself needs to be really well shielded. Grounding of the motor need to be quite well. This is really shittish cable for the laboratory only. You only get away with it because it's short lengths. It's really super important that you have a good grounding system of motor, drive, control system. You will get a lot of noise and problem with signal quality if the grounding is not correctly. Usually we ground the signal cable here in the drive end and not in this end. This end is grounded by the big grounding connection back to the drive. Functionality test, scaling, and also a look at the noise from the resolver signal. On NcDrive, I show my output frequency from the drive. I look at the encoder 1 frequency, which is the raw signal coming from the resolver. On the parameters, I show expander boards, opt BC board, and the parameters related to the resolver. If I have a chance to turn on the shaft, I would see if there is a signal coming at all. Yeah, the green one here shows there is some signal. Then we look at the scaling. If we start the motor now at a specific speed, 50 Hertz. At 50 Hertz from the drive, I read encoder frequency minus 60. Something is wrong. Here the thing that I need to adjust is the direction of the resolver signal. Aha, the minus disappeared, but still 60 is wrong, and that is related to the resolver poles. I know that it's a 6-pole motor, so I need to select between 5 and 12 poles. So here, now it's correct. When I reverse, ta-da, now I can see that output frequency is identical to encoder 1 frequency. I want to see that. What about noise? Take a look at quality of the signal. Aha, I can see here that my green signal is not identical to the output frequency, so there is a small noise here, and that is probably related to my grounding and shielding of the system. We can tolerate some, but not too much. Is there some filtering? Yes. Go to the motor control, and here is encoder filtering time. I think 4 milliseconds is a good starting point for most industrial application with long cables and big motors. Also, the speed error filtering can be set to something. That is the result coming out of the speed controller, so it can also be dampened a little bit. So these two, you can dampen some cable problems, but it's limited how much you can do it. Before going to the closed loop with a resolver, the drive needs to know the relation between the magnet position and the resolver position. We do that with an encoder ID run. And here on the PMS shaft position, we will see a number coming up when we do this identification run. We can see what's happening here on NcDrive. We go to basic parameters. We select identification of the encoder, like this. And we hit the start button. Something happening, there was some current, something going on. We were in the run status, and let's see. Aha! Suddenly it updated the shaft position and there was no faults. So now we had a successful identification of the resolver, and it measured what is the relation between the magnets and the resolver. Now with the encoder identified, we can go to the motor control, and instead of frequency control, we select number 3, the closed loop speed control. In the speed control, there is amplification and integral time of the speed controller. Now it's set for induction motor, 30 and 100. I know by experience that it should be 6 on the KP and 200 on the TI for most all normal permanent magnet motors. But we can just for fun start, see what's happening when we start the motor now. When we start the motor, we see that the current is really small, 0.6 something, but the torque is a little bit fluctuating, and that is the speed regulator. It's a little bit provocated by this setting. It will run, but listen. This is oscillation caused by my settings here, and the torque is a little bit. Sometimes you can see and hear the motor like we do, easy. But sometimes you sit in another place than the motor is. You are in the drives room and the motor is down in the thrust room. Then this motor torque flying all over the place is kind of signal that something need to be tuned. I go with this KP from 30 to 6 and listen. Smooth. Speed control TI should be 200, then you are pretty soft and nice. That means 200 milliseconds to increase the torque 1%. So that is the rate that the integral part of the regulator will do. It's a pure magnification and integral part. There is no derivation part in this regulator. So basically we now have a nice running closed loop control. So this was it. And look at these dynamics. It can act almost like a servo, shifting direction in 0.2 seconds we have now. Can easily go very high speed. We now have a smooth running closed loop control, and we can see this here by shifting direction from plus to minus very fast. You can only do this when the mechanical process allows it, and you have a stable DC voltage and an active front end. Look at my DC voltage, it's relatively stable. What happens if I stopped my active front end? There is no regenerative place to go. I stopped my active front end, and if I try to brake now, what will happen then? Ew. The DC voltage went up in over voltage controller area. My torque all over the place, so I didn't like that DC voltage went down to 580 and there was no place to go for regenerative. So let's start active front end and we have a happy drive again. Ta-da! And then we can run like a Tesla car, Formula 1 car. It's actually a very similar motor standing here, which is in the Tesla 3, I think. So this is the response in these motors. It's really impressive. But it's only in closed loop you will find this performance. The closed loop motor control with encoder or resolver is brilliant for winch control, for the torque calculation and torque limits. We will now have a demonstration of how accurate actually is the torque limiting here with a blocked shaft. So I have put a torque limit of 10% of the motor nominal. So here you can see the torque limit, and this will be the actual torque. The current. When I start with a speed reference of 0, it means sit, put, don't move the shaft, and it only need nothing current to do this. The speed controller basically only sets out the current needed to do the speed that you are ordered. Okay, let's order 1%, and remember the shaft is blocked. It goes to 10% because that's what's ordered. It uses 3.1 ampere to do this job. Let's say I want this winch to pull a little bit harder in the cable, 15%. And here you can see the limit and the actual torque is within 1/10 of a decimal. That precise it is. The current now went up to 4.6. With my blocked shaft I cannot go higher than the 15%, but here you see the resolution. What if you go in the other direction 1%? It can still figure out what is a 1.1, 0.9 of the motor torque when we limit it to 1%. So the resolution and precision in these motors and these resolver feedback is pretty good. And for winches this is really brilliant to keep a constant tension in cables. To get a touch and feel with the torque, here is a free shaft. We now started with a speed reference of 1 and a torque limit of 1%. We can now still move the shaft. This is 1% torque limit. When I increase the torque limit to some 10%, there is no possibility that I can move the shaft. 15%. Back to 1%. And now the torque is a constant tension on the cable, which is just a few kilos. Now for the sensorless closed loop, let's remove the resolver board completely, so it's almost like a rim thruster or any application. There is no sensor or resolver or encoder out there. We have now removed the OP-BC board and the signal from the resolver. We are going to set up the IF control. The parameters needed to do that, the motor control have to set to frequency control because there is no resolver there right now. Enable IF control on this parameter and advanced options to 2. Bit number 9 has to be set high, that is decimal value 512. What is IF control? We select a frequency, and below that frequency there is a current controller setting out the current that we decide. I have set 75% of motor nominal, which is 23 ampere, just so it's easy to recognize. Then when we hit 10 Hertz, it goes to the UF curve open loop, which is about 14 ampere, just to see this nice transition. Motor control mode to frequency control. The IF start is enabled. The current at IF is 75%, which is 23 amperes in this case. IF control limits is 10%, which is 10 Hertz in this case. Let's do a ramp of 10 seconds, and then we see the ramping up, what's going on. And here we saw there was a transition from 23 amperes to 15 amperes. Let's just stop it there and see how it looks on the graph. Here we see what's going on, IF startup with a UF curve. Here we have the current going up to the ordered 23 ampere, and when we are passing 10 Hertz, it goes down to 14.6, which is the UF curve current. Here we see the Greenhorn modulation index and also the motor voltage going up to the field weakening point. Here the voltage actually work a little bit to have the current controller exactly on 23 ampere. Here we see the motor torque go up in the startup. So this is a nice thing to just pull the magnets and get a firmly startup. And here we see hitting the 100 Hertz away into the field weakening point, and the current go down according to the UF curve. So this is our IF startup with UF curve on 10 Hertz. Now we have come to the juicy part, sensorless closed loop setup. Parameters: put the encoder supervision to warning, and also the advanced option 1, set bit number 2. Then we leave the warnings from the hardware encoders out of the speed controller. Also set the start angle time to 50 milliseconds because the default value 0 might cause some startup problems. Then perform identification run dead time compensation, which means the drive will then measure the real time delay and response time in your hardware. We are using the same software for a big drive as for the small drive, and this will determine the differences. Then put advanced options 2, bit number 0. We already have set bit number 9, so the value sits at 512. It should now go to decimal 513. And this allows you to select motor control to 5 sensorless. And here we go. That's all the parameters. What to expect? We will start up in our IF control. We have already set the current to 23 ampere, a little bit big, but easy to see. At 10 Hertz, it will kick in its sensorless closed loop. The current will go to very low, 1 ampere, 2 ampere or something. And only when there is a load on a shaft, there will be a current of any significance. And I expect the performance and behavior of the drive to be very, very similar to when we had the hardware encoder in the closed loop. So the only difference you will see here where you put the IF control. How low can you put it? 5 Hertz, 7 Hertz? Depend on your load, how hard it's to start your ship propeller. A rim thruster, which can be a lot of friction, might be needing a high current, and a process which turns very easily, then you can have a lower current. Description of these bits I set in the advanced option. You find the application manual for the marine application. Here advanced option 1, where you disable encoder fault on the bit 2. On advanced option 2 you find the sensorless control for PMS motors on bit 0 and IF control on bit 9. In the application here, I start up with 4 and 512. I haven't turned on the sensorless before I have done the DTC. I do the DTC first. In protections, I have turned off the encoder fault. I put it to warning down here. Encoder supervision to warning. I have in motor control set the start angle time to 50 milliseconds. Okay, now we are basically ready to go for the identification run, and here we should select the DTC ident. Let's hit the DTC ident and then the start button and see what's happening. You went to run, something is happening here. It's a current of 10 ampere, something quite different than the IF current that is 23 ampere, 21, 22 ampere. So it's obviously measuring some stuff here now. Start doing some stuff. There is a big reactive current going on. Important that the DC voltage is high when you do this identification run. Take some time. Here is doing some stuff. Even was a sound. finished. Good. And when I see there is no fault here, it goes out of run, we are good. So now we can put it to sensorless motor control and see how it behaves then. We go to the motor control, we select the 5 sensorless speed control, and now we should be able to start it up. Okay, we started up in IF control. Let's just pull it to full speed and see what's happening. There is a 10-second ramp here now. The current is quite high because it's the IF control. And now, look, the motor current went down to almost nothing because after the IF part, it went down to the sensorless closed loop. Looking at this startup, here we see the IF controlled start, and at 10 Hz it goes to the sensorless closed loop, 23 amperes, and then here at about 10 Hz it kicks in the sensorless closed loop. And now the current is very low, it's very efficient motor, all the way up here, full speed, full voltage, and then we go down in speed, and at 10 Hz then the IF control kicks in again, so we are back on IF. In sensorless closed loop with the IF around 10 Hz, what should you expect of dynamics when you change the direction very abruptly with a ramp time of 0.2 seconds? Actually, it responds really well. You can shift direction in 0.2 seconds. Is it usable for winches? No. Around 0 speed, the torque control is not precise enough, I would say. But for dynamic purposes, yes, it's really dynamic motor now. Now it gets even more juicy. We go to overspeed 1.5 times. At 100 Hz, this motor is nominal 500 volt. At 150 Hz, the back EMF is 750 volts. This drive cannot give that. I don't have the DC voltage for it, and the drive cannot give 750. So what will happen? What will happen is that the drive will use its reactive current and manipulate the motor to push back the back EMF. We will see a motor voltage of 500 volt constant, and the motor will spin up to 150 Hz using a lot of reactive currents. We will see this on the ID actual current, and the total current also will go up quite a lot to suppress the back EMF. This is very similar to what happened in a Tesla 3 car. You can see on YouTube videos how the motor is described there, but this Editron motor is not very different from the Tesla 3 motor in that behavior. Let's see how this looks like in real life. The only parameter I have changed in the drive now is the max frequency, so I will allow it to go to 150 Hz. So when I start it now and pull up here to the full speed, it will in a 5-second ramp go to 150 Hz output frequency. The motor current now sits at IF current. First it will go down to sensorless closed loop, very low, and then at field weakening point the current will start increasing. And notice what's happening with ID actual at this point. Okay, here we go. No hands. And here we are in the sensorless closed loop, 120, 140, 150. Here we sit at 150 and an ID actual of minus 390. Here's the curve. So let's have a look on how this looks like. What did we just see overspeeding? We saw that the motor went to 150 Hz. That is 50 more than nominal. Nominal is 100 Hz. And the motor voltage sits constant at 500 volts. Still the motor runs. What actually happened here? If we measure back here, this was the IF startup. Here we see the ID actual, the reactive current going in this direction. And we sit there at IF. Then it starts rotating, spinning. 10 Hz, it goes to sensorless closed loop. Everything is very smooth and nice. The current is very small. And then what happens here? We are hitting 100 Hz. We are into field weakening point. And now we can see that the motor current start increasing. And here, the reactive current go over to the minus side. It's using now the reactive current to suppress the back EMF from the motor. So it sits up here. and suppressing the motor BMF with this minus reactive current. The total current is 12 ampere, and this is a thing, because if you hit a current limit now, let's say you don't have the current needed to do this reactive suppression, that could be an extremely unstable motor. What happens if you stop the active front end here? You will get back 750 volt AC on the motor cables that will pass through the IGBT freewheeling diode straight into the DC link, and voila, you got 1000 volt on a DC link, destroying the drive. So having a trip of the drive here in this situation probably will damage your drive quite severely. So this situation is it's physically possible to go up there, but it's with a risk. Last thing for this episode 5 is to demonstrate what happens when you go overspeed and the active front end stops. This is a don't do this at home. We can do it here on the simulator, but don't do this in a full-scale system. It will maybe destroy the winch and the motor and drives and everything. So what's happening here? We are starting up, and now we are going to have a shutdown of the active front end that produces a stable DC link. Yeah, you could hear something really bad happened. Let's see what happened. First of all, the blue line, when the DC voltage dropped, it went sky high after. We went to 900 something voltage, and this drive have a nominal of 675 volts on the DC link, so this is way too much. All torque voltages, everything went haywire, and imagine what impact this have on the mechanical side, on a winch, on a motor and everything. The drive sits in over voltage, my active front end also is in fault, over voltage, so this is a very brutal thing. So going into the overspeed area, then you basically are up to the active front end that everything is running, so it's a calculated risk. Thank you. This was all for episode 5. See you next time.